Hello friends, welcome to engineering tutorial. From this video we are going to discuss some numerical problems on thermal expansion. Okay, so here it is the first question which is given. It is given that railway lines are laid with gaps to allow for expansion. If the gap between two rails, each which is 66 meter long, the length of each rail is 66 meter, and the gap between the two rails is 3.63 centimeter at a temperature of 10 degrees Celsius. Then at what temperature will the railway lines touch? And it is given that the coefficient of linear expansion alpha for the metal which is used for the railway line, that is equal to 11 into 10 to the power minus 6 degrees Celsius inverse. Okay, so first this question is on thermal expansion but in the linear expansion category. Okay, expansion along a single direction in one dimension. Now it is given that railway lines are laid. Let's say there are two railway lines. Okay, the length of each is 66 meters, the initial length. Okay, the initial length. The gap between them, that is equal to 3.63 centimeters. Okay, 3.63 centimeters. Now, so the gap between them is 3.63 centimeters. So the initial temperature is 10 degree Celsius. Okay, this T0. So you can use this as Li, you can write it as Li or L0, Ti. Finally, you can use subscript Tf or any other T dash. So it's up to you. Okay. So the initial temperature is 10 degrees Celsius. So as the temperature will increase, each of these rails, they will expand linearly as per this linear expansion coefficient, and the expansion will happen for both the rails. Both the rails, they will expand. So the gap between the two rails, it will filled when both the rails, they expand by half length of the gap between the two rails. Okay, let's say this is the separation distance. Okay, this d is equal to 3.63 centimeter. Suppose this rail expanded by d by 2 and this rail also it expanded by d by 2. So they will meet when both the rails expand by half of the separation gap between the two rails. So the increase in the length of the rail which is required is equal to 3.63 centimeter by 2, which is equal to 1.815 centimeter. Okay, or 1.815 into 10 to the power minus 2 meters. Because everything is meter, so it's better that we convert it into meter. Okay, so here the change in length that we require is this. Now we know that the increase in length delta L is equal to alpha L0 delta T, where delta T is the change in temperature. Let's say the final temperature is Tf. So Tf minus T0, that is equal to delta T, which is the change in temperature. So the change in length is directly proportional to the linear expansion coefficient, the initial length, and the change in temperature. Okay, so this is the proportionality coefficient, the linear expansion coefficient, thermal expansion coefficient. So here we will calculate delta T. Delta T is equal to delta L by alpha L0. Okay, this. So now we'll simply substitute the values. So the increase in length which is required to fill the gap is both the rails, they expand by half the separation gap. So delta L is 1.815 into 10 to the power minus 2 by the linear expansion coefficient, which is equal to 11 into 10 to the power minus 6 per degree Celsius inverse, and that is into the initial length, which is equal to 66 meters. So it is coming around, if we calculate, the change in temperature is 25 degree Celsius. So this is the change in temperature, delta T, which is equal to final minus initial, that is equal to 25. But we have to calculate at what temperature they will meet. So we have to calculate Tf, the final temperature. So Tf is equal to 25 degrees Celsius plus the initial temperature. The initial temperature was 10 degrees Celsius. So 25 plus 10, that is equal to 35 degrees Celsius. So at 35 degrees Celsius, both the adjacent rails, they will expand by half the separation gap in towards each other and finally meet at 35 degree Celsius. Okay, this. So initially at 10 degrees Celsius, final temperature at 35 degrees Celsius, both the rails will expand linearly and meet together at the point and fill in the separation gap. This is the reason why when railway lines are laid, some gap is left in between them, okay, to account for the thermal expansion. Okay, so this is the first question which we have discussed. So here is another question on thermal expansion of materials. It is given that a metal ball of radius 0.1 meter is heated from 273 Kelvin to 348 Kelvin. Calculate the increase in surface area of the metallic ball. Given beta, which is the thermal surface expansion coefficient, that is equal to 0.000034 Kelvin inverse. Okay, so here it is given that for the metal ball, the initial radius R0 is equal to 0.1 meter. So the initial surface area will be equal to 4 pi R0 square, which is equal to 4 pi 0.1 square. Okay, let's keep it like that. Let's not calculate it. Okay, so the initial temperature is equal to 273 Kelvin and the final temperature is equal to 348 Kelvin. So the increase in temperature, the change in temperature, Tf minus T0 equal to 348 Kelvin minus 273 Kelvin. Okay, this is the change in temperature, which is equal to 75 Kelvin. This. Okay, now we know that the increase in surface area delta S, which is equal to the final surface area minus the initial surface area, that is equal to beta, the surface expansion coefficient, S0, the initial surface area, and delta T, which is the increase in temperature. Okay, so simply we'll substitute the values here. So it is equal to beta, which is equal to 3.4 into 10 to the power minus 5, initial surface area, which is equal to 4 pi 0.1 whole square, and change in temperature, which is equal to 348 minus 273, that is equal to 75. Okay, this. So it is coming around 3.206 into 10 to the power minus 4 meters square. This is the increase in surface area of the metallic ball. Okay, this, the increase in surface area of the metallic. Okay, so very simple and straightforward, and this is this.